All right, let's look at your new Unit 2 stamp page. My intention was for your first stamp to be the activity on pages 62 to 63. Depending on if you had time in class or not, Miss Woodlock may be changing that for you. So that was my intention, but you may or may not have had time in class for that. Regardless, the day of the 12th for A days or the 13th for B days, your stamp is going to be completing, let me double check the page before I have you write this down. Okay, yeah. Page 66. And then a separate stamp for page 68 and 69. Yes. And then you may not have full time on the 12th or 13th to work on these, because you are also going to do a lab activity on the 12th or 13th that you definitely have to complete in class that day. And that's going to be a lab from pages 70 to 72. And then you may need more time for these two on a different day, but you should end up overall having time to do these, just may not get them all in on the 12th or 13th. You may have to come back to them on a different day. It just sort of depends on how much time you have, just based on what Miss Woodlock thinks. So this is my intention for your stamps. Miss Woodlock will, of course, edit these based on how long or short you guys take to do things. Okay, let's look at page 64. Page 64 looks like this. And we're going to talk more in depth about the structure of the atom. Everything is made of atoms. Atoms are the identifying part of matter. We can use atoms to identify what kind of matter we have. Atoms contain a dense nucleus surrounded by an electron cloud. So here is a planetary or Bohr model showing that. And again, as we move through the year, we're going to find that atoms don't really orbit the nucleus the exact same way that planets orbit the sun. But for now, we're going to kind of pretend that they do. Atoms are made up of 3 subatomic particles. Subatomic meaning smaller than the atom. You got protons, which have a +1 charge. They are located in the nucleus. There are 2 ways we can abbreviate protons. You can do it as either just a P with a plus sign as a charge, or you can write a lowercase p with a little 1 up top and a 1 on bottom in front. When you write stuff this way, the top number is always the mass, and the bottom number is always the charge. If it's usually the number of protons. Oh, sorry, that's off screen. So the bottom number is your charge or number of protons, and the top number is your mass. So a proton has a mass of 1 and a charge of 1. And again, the mass of a proton is 1, with units of what we call atomic mass units, AMU. Atomic mass units. Neutrons have a 0 charge. They are neutral. They are located in the nucleus as well. And normally you could do a lowercase n with a 0 for a charge up top like that, or you could do it in the same other notation where you have a mass of 1 and a charge of 0, and then a lowercase n. So mass is still 1 AMU for a neutron. Electrons have a -1 charge. They're not located in the nucleus. They are in the cloud, the electron cloud. We can abbreviate them as a lowercase e with a negative sign written after it, like a charge. Or you can do an e and have a mass of 0 on top and a charge of -1 on the bottom. Electrons have an approximately 0 AMU mass. They don't actually weigh nothing. They do have a mass. It's just so small it rounds to 0. It's like 0.000001 kind of small. Where compared to a proton or a neutron, it basically weighs nothing. We can find information about protons, neutrons, and electrons on the periodic table, which we abbreviate PT. When you change just the number of protons, you end up changing the element you're talking about. So when I said earlier that atoms are the identifying part of matter, this is what identifies them. The number of protons identifies the element. If you change the number of protons, you're talking about a different element. If you keep the protons the same and change just the neutrons, you're going to change what isotope you're looking at. It'll be the same element but a different isotope, and we're going to talk about isotopes more in a moment. On the periodic table, all your element boxes look something like this, where they've got a number, a symbol, a decimal number, and a word. So we're going to label what each one of those things is. This top one is the atomic number. And then you've got your element symbol is the abbreviation. We talked about those starting on literally the first day of school. Then you've got the average atomic mass. And the element name. And if you ever forget that that's what those things are, there's actually a legend on the periodic table on the back of your book, as well as on the periodic table you receive during a test. There's a legend that tells you what's what. Atomic number, symbol, atomic mass, and name. Of course, you're still responsible for knowing what all those vocabulary words mean. The atomic number is a number that tells you the identity of the element. It is your number of protons. That's really important, that the atomic number is your number of protons. The average atomic mass is an average of all of the masses of all the elements, isotopes. We're going to talk about isotopes more later. The average atomic mass is the mass found on the periodic table. Atomic mass is different from mass number of an atom. Mass number is your number of protons plus your number of neutrons, and it is not on the periodic table. That is really, really, really important. It is not on the periodic table, mass number, not on the periodic table. It is your number of protons plus your number of neutrons, and it is not on the periodic table. It is different from the mass that is on the periodic table. These masses on the periodic table are averages: 28.09, 55.85, 50.94, 101.10. Those are all averages. Whereas mass number is not an average, it's always going to be a whole number, an integer. Whereas the one on the periodic table is an average and will be decimals. So you cannot, if I ever ask you for mass number, you cannot just take the mass off the periodic table. Those are two different masses, two different numbers. Moving on, the element symbol is the shortened element name. It always starts with a capital letter. We talked about that on the first day of school. And then, of course, your element name is the identity of the atom. When you're done writing that, you can turn your page to page 65. And we're going to talk about the ape man. Ape man. Ape stands for atomic number equals protons equals electrons. Those are the same as each other. Now, later in the year, we're going to find out that electrons are not always the same as protons, but we're going to pretend for now they are, because when your protons and electrons are equal, when this is true, when protons and neutrons, or excuse me, when protons and electrons are equal, then you have an equal number of positives and negatives, which means you have a neutral atom. You have a neutral atom at that time. And hang on, sorry. Hello? Hi. Okay, well, I'm recording right now, so if you figure out why you were calling, can you text it to me? Yeah, I did. You did text me? Oh, I didn't see your text because I've been recording. After, and as soon as I finish recording this, I'm going to drive down there, so we'll probably be like 12:15. Okay, cool. Yeah, I will. Okay, bye. That was awkward. I'm not going to cut that out of the video because I don't have those kind of skills. So you're just going to hear me having half a conversation with my husband when you watch this in class. Cool. Okay. Anyway, an ape man tells you atomic number is equal to your protons equal to your electrons. Man stands for the mass number equals your atomic number plus your neutrons. Atomic number is protons, so protons plus neutrons are atomic number plus neutrons. That'll find you the mass number, which again is different from the mass on the periodic table. So, one more time. Your atomic number is your number of protons. It tells you the identity of the element. And assuming you have a neutral atom, which we're going to do for this whole unit, it will also be equal to your number of electrons. So that's your ape, A-P-E, an ape man. And your mass number is equal to your number of protons plus your number of neutrons, or number of protons and atomic number are the same. So number of protons plus neutrons or atomic number plus neutrons, that's where the man comes from, M-A-N. in Ape Man. It's a memory trick. And of course the mass number, still not the thing on the periodic table. Not the thing on the periodic table. If your mass number is protons plus neutrons, that means you can find protons by doing mass number minus neutrons. Or you can find neutrons by doing mass number minus protons. Math. Okay, atomic structure. There's some guided practice here. We're going to go through a few questions. What element has 47 protons? Remember, the number of protons is equal to your atomic number. So what you got to do is go to your periodic table and find atomic number 47. So flip to your periodic table that's on the back of your book. Find element number 47. And that element is silver. A neutral atom has 8 electrons. What element is this? We know that thanks to Ape, the atomic number equals the number of protons equals the number of electrons. So if we have 8 electrons, that also means we have 8 protons, and we need atomic number 8. So if you go to your periodic table and look for element number 8, you find that it's oxygen. For number 3, how many neutrons are found in chlorine? Well, we know that mass number minus or equals the atomic number plus the neutrons. So that means to answer this question, we have to do neutrons equals mass number minus protons. So we need a mass number for this. This question left off the mass number. I'm going to tell you we're talking about chlorine with a mass number of 37. So if our mass number is 37 minus, I'm going to say that's your mass number. So neutrons are mass number minus protons. For chlorine, the number of protons is the atomic number 17. So if I do 37 minus 17, and I get there are 20 neutrons in this chlorine. And what is the mass of a carbon atom that has 8 neutrons? Mass number again. If we're using Ape Man, mass number equals atomic number plus neutrons. That's the M-A-N in Ape Man. So if we're looking for the mass number, we need the atomic number of carbon, and they're telling us there are 8 neutrons. So I go to my periodic table and I find carbon. Carbon's atomic number is 6. So I'm going to do 6 for the atomic number plus the 8 neutrons they told me. That's a mass number of 14. There's also a little chart here where they've given me a little bit of information. I have to fill in the rest of the chart. They've told me a number of protons. If I know the number of protons, I also know 2 other things. According to Ape Man, the atomic number equals the protons equals the electrons. So these 3, atomic number, protons, and electrons, are all equal to each other. That means if I know there are 26 protons, I also know the atomic number is 26 and the electrons are 26. Remember, from Ape Man, the mass number is equal to the atomic number plus neutrons. So my atomic number was 26. Neutrons are 30. If I do 26 plus 30, that is 56 for my mass number. From there, filling in these first 3 boxes should be fairly straightforward, because now if I know it's atomic number 26, I can go to my periodic table and figure out the element name for number 26. Number 26 is iron, and its symbol is Fe. And its average atomic mass, that is the mass on the periodic table. So that is the 55.85 that's right there. Notice that that 55.85 is different than this 56. 2 different numbers. Let's try drawing a couple things. Boron. Its number of protons and electrons we know from the periodic table, because protons and electrons equal atomic number, and the atomic number of boron is 5. So I know that if I'm going to draw a boron, I need 5 protons and 5 electrons. For the number of neutrons, we don't know from the periodic table. You'd have to get told, and I'm going to tell you you need 6 neutrons. So if we're going to draw this, then we need to draw a nucleus, which is what I drew for my first circle here, a nucleus. 5 protons, I'm just going to put 5 little plus signs in there for my 5 protons. And 6 neutrons, I'm going to put in some zeros because neutrons are neutral, no charge, 0 charge, 6 of them. And then if I need 5 electrons, well, you may remember from middle school the first shell can only hold 2. And then the next shell is where the rest of them have to go. So I have 5 total, 2 only in the first shell. So the next shell out is where I'll put numbers 3, 4, and 5. Okay. I'm going to, again, tell you how many neutrons to draw for carbon and sodium here. For carbon, I want you to do a carbon with 8 neutrons. Just like in problem 4 up here. Oh, whoops, that's really blurry. In problem 4 up here, carbon had 8 neutrons, so we're going to do 8 neutrons in the carbon we draw down here. And when you draw your sodium, do one with 12 neutrons. And I'm going to silently do that up here on the video. You should try it without looking. Try and look at only your paper, not at me silently doing it on the video, and then you can check yourself after you finish each drawing. So I'm going to go silent. You are going to try not to look at the video while you draw these 2 yourself. Remember to use your periodic table to figure out how many protons and electrons you need. Okay, my carbon and sodium are done. You're free and welcome to pause the video if you're not done with yours yet. I'll remind you with sodium specifically, the first shell can only hold 2 electrons, the second shell can only hold 8. So that's 10 electrons, you need 11. The 11th one has to go outside in a third shell, which again is something that you probably remember from middle school. Okay. Again, if you're still working or checking, you can pause the video. I'm going to go ahead and turn my page. On page 66 is an independent practice chart. This is for a stamp. Ms. Woodlock, depending on what time it is in class, may pause the video now and have you work on this, or she may have you do it later. I'm going to keep going. Let's look at page 67. Isotopes are atoms of the same element, meaning they have the same number of protons with different mass numbers due to a difference in the number of neutrons in the nucleus. Let me zoom in some for you. Okay, and there is a typo here that we need to fix. It says the mass number on the periodic table. Mass number is not on the periodic table. Atomic mass is what's on the periodic table. So atomic mass on the periodic table is an average of all the occurring isotopes for that element. We're going to talk on a different day about how you calculate that average. It's different than just your normal mean, where you add them all up and divide by how many there are. So we'll talk about that average some more later. But isotopes. We have 3 pictures here. There's hydrogen, normal hydrogen. Then there's deuterium and tritium, which are 2 different isotopes of hydrogen. I know they're all hydrogen because they all have 1 proton. And if there's an atom with 1 proton, that means its atomic number is 1, and it has to be hydrogen. But this hydrogen and this hydrogen and this hydrogen, even though they're all hydrogen, they're still different from each other. The first one has no neutrons. Deuterium has 1 neutron, and tritium has 2 neutrons. So these are isotopes of each other. These 3 are isotopes of each other because they are all the same element, but they have different masses. This is called deuterium because it has 1 proton plus 1 neutron. That is a mass of 2. 1 plus 1 is 2. And this deut right there, I think that's Greek. It means 2. It might not be Greek. It might be Latin or something. I don't know. Tritium has 2 neutrons plus 1 proton. That is a mass of 3. That's what the tri comes from. The mass is 3. There are 2 ways to write isotopes. You can write the name, a hyphen, and then the mass number, I should say. So like carbon hyphen 12 means that there is the element carbon with a mass number of 12. Remember that your mass number, remember ape man, The mass number is your atomic number plus neutrons. So some other examples would be like sodium 25, or like what we drew earlier. We drew boron. When we drew boron, it was with 5 protons and 6 neutrons, so we drew boron 11 earlier. You could also write it in what's called isotope notation, where you have mass number is a little number on top, atomic number is a little number on bottom, and then the symbol. So like 12,6 carbon, where this 12 is your mass number, the atomic number plus neutrons. 6 on the bottom is your atomic number, the number of protons, and then C for carbon. The reason we write mass number on top is so that if you want to find the number of neutrons, it's real easy to just subtract and be like, oh, this is 12 minus 6 is 6 neutrons. So like for sodium 25, sodium is Na. The mass number 25 would go on top. And you go to your periodic table to find the atomic number 11, telling you the number of protons, so you'd write that on the bottom. And then if I asked you how many neutrons, you'd be like, oh, let me just subtract that real fast for you. 5 minus 1 is 4, 2 minus 1 is 1, 14 neutrons. Easy. For boron 11, boron is just a capital B for its symbol. The 11 is its mass number. And you go to your periodic table to find that boron's atomic number is 5. So that's what gets written on the bottom. And again, if I asked you how many neutrons, you'd be like, oh, let me just subtract 11 minus 5, 6 neutrons. Easy. So simple. You can remember what goes where using what we call Big Mac. M-A-C there, where M stands for mass number, A stands for atomic number, C stands for the charge. If there is one, you would write the charge up here. We're not going to be using charges much in this unit. We're going to worry about charges more in Unit 4. But MAC, that can help you remember what to write where. So let's do, again, some guided practice. Carbon 12 and carbon 14 are isotopes. Since both are carbon atoms, they have the same number of protons. All carbon atoms have blank protons. Find that out using, again, Ape Man. Your protons are equal to your atomic number. So you go to your periodic table and find carbon's atomic number. Go to your periodic table. Find carbon's atomic number. It's 6. So there are 6 protons. Carbon 12 and carbon 14 are going to have a different, this blank's really small, sorry, a different number of neutrons, because that's the only way they can get different masses. They both have to have 6 protons. If the mass is, again, mass is atomic number plus neutrons, they're both atomic number 6. If they're going to have different masses, they must have different neutrons. That's the only way you can add up to different masses. So to find carbon 12's mass, from hyphen notation, we know that having it as name hyphen number, that number is the mass number. So this 12 is the mass. Your neutrons are the mass number minus protons, so mass number minus, and we said there were 6 protons. 12 minus 6 tells me there are 6 neutrons. So carbon 12 has 6 neutrons. But carbon 14 is different. This 14 is the mass for carbon 14. So instead of doing 12 minus 6 to find the neutrons, we're going to do 14 minus 6, which gets us 8 neutrons. So carbon 14 has 8 neutrons. That's why they're different masses. And these are isotopes of each other. They're both carbon. They have the same number of protons. But to get different masses, they have to have different numbers of neutrons. Okay, I'm going to turn the page. Page 68 is another page you're supposed to do independently, as is page 69. That's for your stamp. For page 70, this is a lab activity that Miss Woodlock, I'm going to let her walk you through at this time. She either, depending on what time it is, she might have you do this lab right now, which I think is probably going to be the case, or she might give you some independent practice time for those other stamps, but I think probably it's going to be time to do this, and then if you have extra time after you finish the lab, you can go back and work on those stamps today, or you'll have some other time on other days to do it. But regardless, I'm going to pass it over to Miss Woodlock.